click the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on the videos.
Welcome back to another episode of Smart Builders tutorial in the course CEE 3311 separation process. In the previous video, we solved a certain question using the Kremser equation. So in this question, we'll solve another example using the other method. That's the graphical method of solution, which has another name called Mercatial. So let's read the question together. The question says, by means of a plate column, acetone is absorbed from its mixture with air in a non-volatile absorption oil. This is my separation column. This is the first inlet. This is the other inlet. This is the first outlet. And this is the other outlet. This is my inlet, liquid phase, LAXA. This is my vapor inlet, VBYB. This is my liquid outlet, LBXB. And this is my vapor outlet, VAYA. So by means of a plate column, acetone is absorbed. From the question, we are told that it's absorption from its mixture with air. So we are told that the acetone is mixed with the air. So you know that it's going to come through this the vapor phase inlet, right? Here, this phase. So with a non-volatile absorption oil, the liquid that is flown to absorb the vapor or the acetone from the vapor phase is non-volatile oil. The entering gas contains 30 mol% of acetone. So the entering gas, this is VBYB, the mass fraction of the acetone is 30 mol%. So here we are given that YB is 30 mol%, that's 0.3, right? This is the data we are given from the question. The entering oil is acetone free. The entering oil here, LAXA. What is the mass fraction of acetone in here? LAXA, therefore the mass fraction XA is 0. Since we are told that acetone free, we have no acetone. Of the acetone in the air, 97% is to be absorbed. We are given the percentage acetone absorbed also here. Percentage acetone absorbed is what? 97%. You can say 0.97, right? So, and the concentrated liquor at the bottom of the tower, the concentrated liquor, that's the bottom stream of the liquid phase, that's LBXB, we are told that is to contain 10 mol% of acetone. So we are given the mass fraction of acetone in the vapor, in the liquid outlet of the bottom stream here. XB is 10 mol%, that's what? 0.1. The equilibrium relationship, here we are given the equilibrium equation, the equilibrium line equation. YE is equal to 1.9 XE. Plot the operating line and determine the number of ideal stages. You know that we are going to plot a graph like this, the x-axis and the y-axis. Then we have to plot equilibrium line and operating line, of which for the equilibrium for the operating line we are going to have a points like XAYA, XBYB, that is at stream A and stream B. And 2 points will not be enough for us to plot the graph. We will account for plate N in the middle. I've explained this earlier, right, in the previous videos. So in the middle I will account for XN, YN. These are the 3 points that I will use to plot my operating line. But I'm just given this data. Of all the data I'm given, there is no any mass flow rate, either of the liquid or of the vapor. So since there is no any mass flow rate, I'm going to take a basis. What is coming in with the acetone is the vapor phase, right? So let me say the mass flow rate of the inlet of the vapor, that's VB, right? VB, let me take a basis of 100 mol. Let me say basis here. VB to be 100 mol. So let me account for all the data I'm given so that I will know what I'm going to find or I'm going to calculate for. I'm given that XA is equal to 0, XB is equal to 0.1, YA I'm not given, I'm going to account for it. YB is 0.3, and then I'm going to account for what? YN and XN. XN2, I don't know it, and YN. These are the points I'm going to determine for the operating line. So you know that the first thing we have to do is to do the balance. So now I will say percentage acetone, the same balance we did using that Kremser equation. That's the one we are going to do here. Percentage acetone absorbed is equal to, you have to be careful very much at this stage to know that your acetone is coming in through the vapor phase inlet, right? Here, acetone is coming in the vapor, and the liquid phase is coming here. After the countercurrent mixture, the liquid washes away the acetone from the vapor and it comes out here. So we are going to say that the acetone absorbed is going to be the acetone at the bottom stream of the liquid, right? Percentage acetone absorbed is going to be acetone at bottom stream. So since it's acetone at bottom stream, what is the percentage absorbed? I'm told it's 0.97. 0.97 times the inlet of the vapor that comes with the acetone VBYB is equal to be the acetone at the bottom of the stream. At the bottom stream is going to be what? LBXB. LBXB. So I have YB, I have XB, and I also have VB as the basis I've taken as 100 mole. Now I can easily find what's the only unknown in the equation, that's LB. LB is equal to what? 0.97 times VB. What is my VB? 100, right? Times 100 times YB. What is my YB? 0.3 times 0.3 divided by XB. I'm given XB to be 0.1, right? 0.1. So now the value of my LB is what? 291 mole per hour. Here I will account for acetone unabsorbed. I accounted for LB because I wanted to account for acetone unabsorbed. From acetone unabsorbed, that's where I will find the value of my YA. You know, from the unknowns we are defined, see them here, we are defined YA, XN and YN. So to find YA, I have to account for LA first, then I will account for percentage acetone unabsorbed. So doing my account, or my balance, I will say percentage acetone unabsorbed is equal to what? Acetone now at the top stream. Since it's not 100% that is being absorbed, the remaining one that is not absorbed at the bottom stream is going to be at the what? Top stream. Since the acetone, I will account for the 100% of acetone that comes in. 97% of it is absorbed. Now I will have 3% that is unabsorbed. That's 0.03. Acetone coming in is VB, YB is going to be acetone at the top stream, which is what? VA, YA. I have my VB, I have my YB, so now I'm going to account for VAYA. So here I will say VAYA is equal to 0.03 times 100 times what? YB 0.3. What is this? VAYA is equal to 0.9. So now my VAYA is equal to 0.9. How can I find the value of my VA? To find the value of my VA, we know that VB is what comes in, and from VB acetone is absorbed. The remaining part of VB after acetone is absorbed is what goes out to where? Is what goes out as VA. Right? Let's go back to the diagram to explain this. Yeah, here is it. VB comes in, and from VB we don't have anything here at VA, right? Acetone is absorbed. After the acetone is absorbed, therefore the remaining part of VB, the whole VB, that's the air and the acetone, is what goes out here as VA. You get it, right? So let's say now VB is equal to VB minus acetone absorbed is my VA. What is the acetone absorbed? The acetone comes in as 30 mol. So acetone absorbed is 97% of 30 mol. Calculate it in your calculator, press it. This will give you 29.1. So VB is 100, right? Then VA is equal to 100 minus 29.1, which is going to give us what? 70.9, right? So now my value of my VA is 70.9, and we know that VAYA is equal to 0.9. So here I will say YA is equal to 0.9 divided by 70.9. What is the value of my YA? I got 0.0127. So now I have the value of my YA. So now I have XAYA and I also have XBYB, the two extreme points of my operating line. The middle point I'm going to account for is XNYN. So to account for XNYN, I will say, let's go back to the diagram. From this diagram, the acetone coming here at the inlet of the vapor phase is 30 mol%. So as it's coming, mixing with the liquid, some part of it is removed, some part of it is removed, some part of it is removed, until where there is complete absorption. Let's say a certain point around the top of the column before the remaining air and the remaining unabsorbed acetone goes out. At a certain point where there is complete absorption, we are told that the acetone that goes away completely is 29.1, right? So at a certain plate, let's say in the middle, around here, let's call this plate N. At this plate N, some percent of the acetone have been absorbed, have been removed from the vapor phase around this place, and not up to 29.1. The remaining have been absorbed at the upper part of the N. That's when there is complete absorption. We have 29.1 absorption. So let's check a certain number. Let's say at plate N, we have 17 acetone, 17% or 17 mole of acetone have been removed or have been absorbed. So let's say to account for Xn and Yn, we will say let the acetone reaching plate N to be 17 mole%. 17 mole. So my acetone, or the vapor phase of the acetone now, VNYN, is equal to what? 17. This is what I mean by all the explanation I did from the diagram. VNYN to be 17. So what is going to be my Vn now? Vn is equal to, we know that at Vb it's 100 mole altogether that comes in, of which 70 is air and 30 is acetone. So at Vn we have our air still 70, but reaching Vn is not all the 30. It's not all the 30 mole of acetone that reaches N. It's only 17 mole that reaches N. That means 13% of it, or 13 mole of it, have been absorbed before reaching plate N. So my Vn is going to be what? 70 plus this is going to be 87. Since my Vn is 87, I can account for Yn. Yn is equal to 17 over Vn, that's over 87. 17 over 87, that's 0.195. 17 over 87, 0.195. So now I've also accounted for Yn. What remains for me to find my equilibrium operating line delta is the Xn. So to find Xn, since to find Yn I accounted for V and Yn, to find Xn I'm going to account for Ln Xn. Ln Xn. Ln Xn. What is going to be my Ln Xn? My Ln Xn is going to be the acetone that reaches plate N minus the total acetone that leaves the column completely. So let's say here my plate N, here it's what? VNYN, and here it's LNXN. So at this plate N, LNXN is going to be my total acetone that comes minus the acetone that leaves altogether. The acetone that leaves altogether, that's VAYA. We have already accounted for it to be 0.9, right? So LNXN is going to be my acetone that reaches plate N, 17, minus the total acetone that leaves the whole column, 0.9, which is equal to be 16.1. So now I have Lnxn to be 16.1. Then I have to account for Ln. After accounting for Ln, then I will know what my Xn is. So to account for Ln, I will say Ln Xn be equals 16.1. So now we can just say Xn is equal to what? 16.1 over the value of Ln. But we don't know what our Ln is. Back to the diagram, we can directly know what our Ln is. Remember this your column. Here is V and Y incoming from the bottom stream, yeah. And here is Lnxn, that's LAXA at your plate N. That's where you have Lnxn. And now you have Lnxn to be 16.1. So neglecting the mass fraction, now taking care of only the mass flow rate, what will we have at plate N for the liquid phase? You know that completely LA is coming. Yeah, I know to Ln I will have LA and the acetone that will be reaching plate N. We have the acetone, the Lnxn, that's completely the mass flow, and the acetone there at 16.1. So Ln here will be what comes from here and the remaining portion of acetone, yeah, you know, that reaches the plate N. That's my 16.1, right? So therefore I will say Ln will now be equal to La plus what reaches that plate? That 16.1. 16.1. So did I have La? But if I don't have La, I can also account for it. Back to the diagram again. Is La coming in altogether, but I don't have the value, or I don't have the molar flow rate, but I know the molar flow rate of Lb, what's coming in, right? So I know that complete La that comes in is what goes out through Lb, but plus what? Plus what has been washed. Yeah, you know, La plus the acetone that have been absorbed is what comes out of Lb. So now I can find the value of my La. Yeah, La will now be equal to Lb minus acetone absorbed, because Lb is what comes in. Starting by this, Lb is equal to La plus acetone that have been absorbed. Acetone absorbed. Therefore, La is now equal to Lb, which we have calculated earlier to be 291, right? Minus 29.1. Therefore, my La is now 261.1 29.9. 291 minus 29.1 is 261.9 mole per hour. So now I have found the value of my LA. So Ln is equal to LA 261.9 plus 16.1, which is equal to 278. So now I have the value of my Ln also, so I can find Xn directly by saying Xn is equal to 16.1 divided by Ln, which is 16.1 divided by 278, which is equal to 0.058. So now I have all my values that I can use to plot my operating line, meaning. So now XA, YA, I have them to be what? XA is 0, acetone free coming in, and YA is 0.0127. Then XN, what I've just accounted for, XN is 0.058 and YN is 0.195, already accounted for also. Then XB and YB, the other extreme end, which have been given from the question as 0.1 and 0.3. So now this is what I have to plot my operating line, right? So to plot my equilibrium line also, to plot the line, we are going to plot equilibrium line and operating line in the same graph. We are given so the equation of equilibrium line to be YE is equal to 1.9 XE. YE is equal to 1.9 XE. Since YE is equal to 1.9 XE, you know that we are going to be defining the value of our XE, multiplying it by 1.9, that's the slope, to get our YE. So let me plot draw a table like this, saying XE is equal to here YE 1.9 XE, taking 0 as origin. So I know 0 times 1.9 is 0. So I will be putting my line, the values of my X that will correspond to the values of my X I have here in the operating line values. In the operating line values, I have 0, I have 0.058, I have 0.1. So to determine a point so closer to this, let me take a range of 0.05. I need to determine my X at 0.05. I need to determine X at 0.1. I need to determine X as 0.15. Let me determine the values of my Y to see if they will be enough for me. So here at 0.5, 0.05, I will have what? 0.095. At 0.1, I will have 0.19. At 0.15, I will have 0.285. So comparing with the values of X and Y I have for the operating line, I have 0 to 0.1 here too I have X 0 to 0.1, but for the operating line I have something up to 0.3. So I need to determine in my equilibrium line something like 0.3. I have to have 0.3 and above in my operating line. So here I need to say 0.2 additional. Then this will give me 0.38. So here I have 0.38 and there I have 0.3. Now it's okay for me. So to determine the number of stages, I will plot. This is a graph of X and Y axis. Yeah, a plot of on this plot I will find out where my values of X and Y for the operating line are. I have something like 0. Yeah, after finding the values, I will plot my operating line. After plotting my operating line, the same thing for the equilibrium line. On the same graph, I'm going to plot that equilibrium line. After plotting the equilibrium line, I will start accounting for the values. So if you plot it, it's going to be something like this. Yes, this blue one is the operating line having the 3 points, x, a, y, a here, x, n, y, n here, x, b, y, b here. While this red one is the equilibrium line, having the values from the table. So after doing this, you will just be plotting your triangles. I told you from the operating line to the equilibrium line, draw a horizontal line. As it touches the equilibrium line, draw a vertical line upward. As it touches the operating line, draw a horizontal line. As it touches equilibrium line, draw a vertical line until or up to the last part of your operating line. Up to the last part where the triangles of your operating line. So then you count the number of triangles, and the number of your triangles will be equivalent to the number of ideal stages you have. Therefore, you have something like this. This is it. Something like this. This is operating line. And the other one is the equilibrium line. This one, you'll be plotting up to the end like this, where n is. This is the end of your where equilibrium line and operating line merges with your triangle. So the number of triangles you have is equal to the number of ideal stages. So that's all for solving number of ideal stages using the graphical method or the McCabe-Thiele method. If you have any question, comment, or misunderstanding from the question, you can state it in the comment section. That's all for absorption and stripping using Crimson equation and using graphical method.